Engineers almost invariably need to use measured data to perform their jobs. For example, data are used to create mathematical models that we can use to analyze systems. Verifying that a system we've built meets design requirements is also invariably done using measured data. In this demonstration, we'll explore some data measurement issues. To do this, I'll use an acoustic proximity sensor to measure distance. The sensor isn't particularly well suited for the purpose I'm using it for, so I'll use some add-on circuitry to overcome some of its shortcomings. Before I start this demonstration, I'll introduce some terminology relative to instrumentation systems. Any measurement starts out with a sensor. The sensor converts what's being measured to a form that can be used in an electrical circuit. Photoresistors, for example, respond to a change in light level with a change in resistance. All information is represented by voltage levels, since voltages can be easily transmitted and recorded. This means that we'll usually need some additional circuitry to convert the sensor output to a voltage. This is a photoresistor. I'm using this DMM to measure its resistance. Under light conditions, it's got about a 2 kilo ohm resistance, but if I cover it over, the resistance goes up to about 17 kilo ohms. I can convert this resistance change to a voltage change by connecting this photoresistor to this resistor here and applying a 9-volt difference using this battery across the two. If I measure the voltage across the photoresistor using this DMM now, under light conditions I have about 1.3 volts. If I cover it up, that voltage changes to about 4.5 volts. So I've converted the light level change to a voltage change. Even after the sensor output is converted to a voltage, the data will probably contain undesirable components. Therefore, any instrumentation system will also usually include what is called signal conditioning or filtering in an attempt to rectify these shortcomings. For example, one common problem with any measurement is the presence of noise in the data. Noise is variations in the measurement that have nothing to do with the parameter being measured. One goal of filtering is usually to remove noise from the measurement. Another goal of signal conditioning is to increase the sensitivity of the measurement. The sensitivity is just the rate at which the voltage changes relative to the change in the measured parameter. Thermocouples, for example, produce a voltage when their temperature changes. However, the range of voltages they produce are very small, so the sensitivity is measured in millivolts or microvolts per degree of temperature. In order to make the voltage variation with temperature usable, the sensitivity of the measurement has to be increased by a signal conditioning circuit. This is a thermocouple. All it is two different wires made out of different metals that have been joined here. If I change the temperature of this junction between these two metals, I should get a voltage out of it. So let me connect my DMM to measure the voltage across this terminal. I get about minus 0.097 millivolts at room temperature. If I warm this up by gripping it between my fingers, I get up to about a half a millivolt. I do get a temperature change out of this by warming it up. It's just not a very big change. Finally, one common purpose of signal conditioning circuits is to increase the power of the signal. Sensors such as the piezoelectric sensor in the power amplification project often don't produce enough power to allow the signal to be transmitted or recorded. The filtering system often increases the power output of the system while reducing noise and increasing the sensitivity. Now let's take a look at the data produced by an acoustic proximity sensor and see why we need these added circuitry to perform these actions. This is a close-up of the acoustic proximity sensor. It emits an ultrasonic pulse and measures the echo of the signal. The elapsed time from when the pulse is emitted and when the echo is received is used to estimate the distance between the sensor and the surface causing the echo. There's circuitry in this module that converts that elapsed time to a voltage. This is our system. We're going to use this acoustic proximity sensor to measure the distance to the bottom of this platform. I'll use a USB-based oscilloscope to measure that distance. The sensor will measure the distance to the bottom of this platform. Unfortunately, the sensor is intended to measure a much larger distance than these, so the voltages produced by the sensor will be small. I've connected my USB-based oscilloscope to the sensor to record its output voltage. I'll start the oscilloscope acquiring data, stretch the spring, and release the platform. The platform moves up and down, and the voltage out of the sensor tracks this motion. Unfortunately, the output voltage levels are small, only about 0.2 of a volt over the entire range of motion. If the entire range of motion is about 15 inches, this means that the sensitivity is about 0.2 divided by 15, or a little over 1/100th of a volt per inch. This will make it hard to actually measure small displacements since the related voltages will be so small. Another problem is that there's a lot of noise in the signal, which is causing this jagged stuff in the signal itself. This noise is just random fluctuations in the output voltage due to non-repeatable outside influences. I can see it a little better by zooming in on the time scale. Notice that the noise changes much more rapidly than the platform moves, so the noise is said to have a much higher frequency than the actual data. To fix these problems, I'll create a circuit that will increase the voltage levels indicating the platform position while decreasing the noise levels. This is a schematic of the signal conditioning circuit we'll use. The output of the sensor is applied across these terminals, and the filtered data is measured across these terminals. This circuit's called a low-pass filter because slowly changing or low-frequency voltages will be passed through the circuit from here to here, while rapidly changing voltages will be stopped by the filter and won't make it to the output. This means that the circuit will reduce voltage levels that are changing rapidly, the high-frequency noise, and increase the slowly changing voltage levels, the low-frequency data. This is our filter. The sensor is connected here, and the output from the sensor is measured across these terminals here. I'll also measure the sensor output before it's filtered so that we can see the difference. I'll start acquiring data using the oscilloscope. I'll displace the platform and release it. The yellow line on the scope is the output from the sensor. The blue line is the output from the filter. The vertical scales on these two lines differ by a factor of 10, so the blue line voltage is 10 times that of the yellow line. That means that over my full scale of displacement, I'm getting almost 2 volts difference. If the displacement is about 15 volts, that means that I'm getting something more than 1/10 of a volt per inch, which is a pretty good sensitivity. Even better, though, is that the output from the filter has been smoothed. It's not having this noise effects that we see on the output directly from the sensor, so it's much easier to work with this smoother data. This project is primarily about information transfer, which is usually represented by voltages in engineering systems. In this particular project, the information was a measured distance, but it was represented by a sensor as a voltage level. Unfortunately, measuring something and representing that information as a voltage can be a difficult task. The goal is to have the measurement respond only to the parameter being measured, but that's nearly impossible. For example, a strain gauge is intended to respond to bending, but they also respond to temperature changes. Disregarding the temperature effects is usually accomplished by an electrical circuit. In the case of this project, the sensor being used had very low sensitivity and high noise. We used our signal conditioning circuit to increase the sensitivity and reduce the noise.